Welcome! Ever wondered how your phone recognizes your face, or how streaming services predict your next favorite show? The answer often lies in artificial neural networks, or ANNs, the digital brains powering today's smartest technology. ANNs are inspired by the human brain, using interconnected neurons to learn from data and spot patterns. Unlike our biological brains, ANNs are clever programs running on computers, designed to process massive amounts of information. They excel at finding connections in data, enabling breakthroughs from medical diagnostics to self-driving cars. In this video, we'll explore how ANNs are built, how they learn, and how they're shaping our world. No complicated math, just simple ideas and analogies to make it all clear. By the end, you'll understand what an ANN is and why it's a monumental leap in technology. Ready to discover how machines are learning to see, read, and understand our world? Let's dive in. To grasp the network's answer. For digit recognition, the output layer might have 10 neurons, one for each digit. The neuron with the highest value is the network's prediction. This journey from input to output is called a forward pass. Weights and biases are the knobs the network turns to get better at its task. The structure, layers, weights, and biases, lets ANNs tackle complex problems. That's how they turn raw data into smart decisions. After summing inputs and bias, a neuron needs to decide what to do next. Enter the activation function, a mathematical rule that transforms the output. Its main job: introduce non-linearity so the network can learn complex real-world patterns. Without activation functions, a network could only learn straight-line relationships, far too simple for real data. The rectified linear unit, or ReLU, is a popular choice. It outputs 0 for negative inputs, and the input itself if positive. These kinks let networks draw curves, not just lines. Activation functions allow hidden layers to build up abstract representations, edges, shapes, even faces. Without them, deep networks would collapse into a single, simple layer. Nonlinearity is what gives ANNs their power to learn from messy, complicated data. It's the secret sauce behind their flexibility. Thanks to activation functions, networks can recognize everything from handwriting to human faces. That's how they make sense of our world. A new neural network starts out clueless. Its weights and biases are random. Learning is all about correcting mistakes, using a process called training. First, the network makes a prediction. We compare it to the correct answer and measure the error or loss. The goal: adjust weights and biases to minimize this loss. Enter backpropagation, a clever algorithm that sends the error backward through the network, figuring out which weights need the biggest changes. It uses gradients, which point in the direction of steepest error increase. To improve, we move in the opposite direction, a process called gradient descent. Imagine walking down a foggy mountain, always stepping downhill until you reach the lowest point. Each step makes the network a little smarter. This cycle, predict, compare, correct, repeats over and over. Gradually, the network learns to make better predictions. Training transforms random guesses into intelligent decisions. That's how ANNs get smarter. Training isn't just about feeding all the data at once. The learning rate controls how big each step is during training too big, and you overshoot too small, and learning is slow. These settings, called hyperparameters, include learning rate, number of layers, and more. Data is split into batches, small chunks that make training faster and more efficient. The network processes one batch at a time, updating weights after each. Showing the network the entire dataset once is called an epoch. Training usually takes many epochs, with the network improving each time. It's like studying chapter by chapter, getting better with each review. Data scientists tweak hyperparameters to get the best results. The right settings help the network learn quickly and accurately. That's how training is fine-tuned for success. Now, let's see where ANDs make a real impact. They power image recognition, tagging friends in photos, spotting tumors in medical scans. In language, ANDs drive translation apps, chatbots, and voice assistants, understanding and generating human speech. Self-driving cars rely on ANs to process sensor data and navigate safely. In finance, they detect fraud by spotting unusual patterns. Scientists use them to discover new drugs and predict molecular interactions. ANs aren't just tools. They're a new way for technology to learn and adapt. Understanding neural networks unlocks the future of AI. The possibilities are vast, and your journey into this world is just beginning. Welcome to the age of intelligent machines. Activation function transforms a neuron's output, adding nonlinearity. Artificial neural network, AN, a brain-inspired system of interconnected nodes that learns from data. Backpropagation, the training algorithm that adjusts weights by sending error signals backward. Batch, a small subset of training data processed at once. Bias, a value inside a neuron that helps adjust its output. Epoch 1, full pass through the training data. Gradient descent, the method for minimizing error by adjusting weights in the right direction. Hyperparameters, settings like learning rate and layer count, chosen before training. Loss function, measures how wrong the network's prediction is. Weight, the strength of a connection between neurons learned during training.